Right, on this video, we're going to talk about systems of equations, and we're going to start with linear systems, which are two or more equations. We're really only going to look at two equations of lines of linear functions. And so before we do any of these, let's just talk about what would be the three possibilities for solving a linear system. And to be clear, what we're trying to do is find all of the coordinates of any points that satisfy both of our equations, which is sort of the equivalent to finding any intersection points of our two graphs, of our two lines. And when we talk about lines, there's three cases. So case number one, if I get two equations of lines and they happen to intersect, I'm going to get just one solution, right? There's no way a line could come back and hit another line twice. So if they intersecting lines, then we're going to get one solution, only one solution. This is for two lines. But of course, another possibility is my two lines could be parallel lines. I could have two equations, they're never going to intersect. And so if the lines are parallel, then of course they will never intersect, which means there would be no solution, no common points of intersection between those two. And then the third possibility is we could have two equations that are in fact the same equation. Maybe one looks a little bit different, but it really is just plotting the same points of another line. So they could be the same line, my two equations. In which case, if we're looking for all of the common points to both equations, this would have infinite solutions. So those are the three possibilities. If we've got a linear system of two equations, the lines are either going to intersect, we'll get one solution, no solution, or infinite solutions. You can never have two solutions or three solutions when we're talking about linear systems. Now let's talk about how we actually find those. So if I've got a couple of equations of lines here, one way to do it would be to graph, although we'll talk about the limitations, but sometimes it's pretty clear where your lines will intersect. Now let's graph this one right here, x plus y equals 4. And when the lines are written in this form, my favorite way to graph the line is to find my intercepts, because I know to find my x-intercept, I'm just going to be setting y equal to 0. When the graph crosses the x-axis, y will be 0. And that's easy to do. If I imagine y being 0, then x is going to be 4. And then I can find my y-intercept by setting x equal to 0. And when x is 0, y is also 4. So if I have plot those 2 points, this is 0, 4, this is 4, 0. I can connect those two. I've got a line here. And for my other equation, my x-intercept, if y is 0, that'll just be negative 0. It's just going to be x equals negative 2. And my y-intercept, if x is 0, I'm going to have negative y equals negative 2, which is going to give me positive 2 for y. So 0, 2 is there, negative 2 zeros right there. And if I connect those with a straight line, then we can see there's one point of intersection. And if we really graph this accurately, you can probably see that it certainly appears that the solution, the intersection point, occurs when x is 1 and y is 3. So it looks like we have intersection at 1, 3. Now, the limitation with graphing is, yeah, it certainly looks like that, but how do we know that intersection point isn't like 1.1, 3.2 or something? I mean, you can't really tell, right? Exactly. So if you do the graphing method, you would at least want to check to make sure that we have the right answers. So how do I check? I'm just going to plug in x and y into both equations. 1 plus 3 equals 4, that checks out. And if I go 1 minus 3, that would equal negative 2, that checks out. So we can be certain that that is our one and only solution. Okay. Now, another way we could solve this, so we have the graph set, we'll use the same two equations, is by the substitution method. So let me rewrite my two equations. X plus y equals 4 and x minus y equals -2. So if I didn't want to graph this, what I could do is take one of the equations and solve it for x or y. It doesn't really matter. I think I'm going to solve this one for y. I'm going to subtract the x over, so it's going to be -x plus 4. And the idea of the substitution method is if I'm looking for the common point between these two lines and I solve one equation for y, I can literally substitute that in for y on my second equation. So that's going to be x minus, now be careful, I'm minusing what I'm putting in for y, which is -x plus 4 equals -2. And if I distribute the negative, that gives me x plus x minus 4 equals -2. 2x, if I add the 4 over there, gives me +2. I get x equals 1. And if I put that right back into here, y equals -x plus 4. If x is 1, that's going to give me y equals -1 plus 4. Y is going to equal 3, which is the same exact point we got when we graphed the two equations. So the substitution method works fine. It's pretty intuitive. Just solve one of the equations for x or y, plug it into the other one. And yet another way that we can solve systems of equations is what we call the elimination method. And there's sometimes this one is maybe a faster way to solve it. So let me rewrite my two equations. When you do the two equations, if you're going to use the elimination method, it's really handy if you write them one above the other. And what the elimination method says is a valid method for solving for the intersection is taking those two equations and I can either add or subtract them from each other. In this case, I'm going to add, because if I add, x plus x gives me 2x, y plus -y is 0, those cancel out, and 4 plus -2 is 2. That gives me 2x equals 2, which means x equals 1. And we already know if you put that back into either one, I get y equals 3. And I would list that as an ordered pair, 1, 3. Okay, so these are the ways you can solve a system of equations. So, and then in truth, as you practice as we go forward in your math career, if you get a system of equations, you can really use mainly the substitution and elimination method. The graphing method's not going to be super accurate all the time, and there might be times you don't want to graph the functions because they're really complicated. So I've got, these are two linear functions, two equations of lines. And I'll sort of what I do, the substitution method, again, is more intuitive in many cases. And so when I look at my two equations, if I see that there's a variable that I can easily solve for, in that top equation, it's really easy to solve for y. I could just subtract the x over. Y is equal to -2x plus 3. Then I'm going to use the substitution method because it's really easy. I can solve that for y and I can plug it into my second equation. So I'm going to get 5x minus 2 times -2x plus 3 equals 1. I'll distribute 5x plus 4x minus 6 equals 1. That's going to give me 9x minus 6 equals 1. 9x equals, if I add the 6 over 7, so x would be equal to 7/9. Okay, well, sometimes that happens. You get a fraction. Now, if I want to know, we're looking for an x and a y value, right? I'm looking for the point of intersection. So to figure out what y is, what I would do is I would plug it right back into here. Y is equal to -2x plus 3. So if this is my x value, I'm just going to plug in 7/9. -2 times 7/9 plus 3 gives me -14/9 plus 3, but I'm going to need a common denominator. So I'm going to think of 3. I'm going to multiply top and bottom by 9. And I get -14 plus 27 over 9. -14 plus 27, I believe, would be 13. So y is equal to 13/9. And again, you can list both of your answers just as an ordered pair because it really corresponds to a point of intersection. Now, when would I not necessarily do the substitution method is for a system like this, because you can see what would happen if, is there any variable on the left side that's easy to solve for without getting some messy fractions? Really, no, right? For example, if I took this top one and let's say I tried to solve it for x, I'd have 3x equals -5. I would subtract the 4y over, and then I'd have to divide by 3. And now all of a sudden I've got fractions, right? And I would have to take this in theory then and plug it back into here. I guess that wouldn't be too bad because I'd be multiplying it by 3. But in many cases, this is going to be tougher, right? We're going to get fractions. And as I've joked in class, even I as a math teacher, I don't really care for fractions. I'd rather not deal with them. So instead, another thing we could do is the elimination method. And one of the things that strikes me about this one is notice that both of these equations start with 3x. And what the elimination method says is, again, I could take these two equations and I could add or subtract them from each other. And in this case, I'm going to subtract because 3x minus 3x is just going to cancel out. Now be careful with the minus here. Then I have to do 4y minus -5y. Really means I'm adding. Minus negative means adding. So it's really 4y plus 5y, which is 9y. -5 minus 13 is -18. And that's easy. That gives me y equals -2. Then what I could do with this is plug it in. You have your choice into either equation. Plug into either equation. So I'm just going to take the top one here. I have 3x plus 4y equals -5. So I'm going to let y be -2. That's 3x minus 8 equals -5. If I add 8, that's going to give me +3. So x is 1. So I'll put these both together. My solution, whoops, why did I say 1, 3? My solution is 1, -2. There we go. Okay. So now let's look at this next one. Once again, it's not going to be easy to solve either equation for x or y without getting fractions involved. And then what also I'm noticing that if I tried to add or subtract one equation from the other, nobody's going to really cancel here. That's not going to make anything better. So another thing with the elimination method is before you add or subtract, you can multiply either or both equation by any constant you want to, and you're not changing the problem. So here's what I'm thinking. If I multiply this equation by 4, and why am I choosing 4? So I'm going to times this by 4, the second equation, because this is going to be -8x plus 20y. I'm multiplying the whole equation by 4, so that equals -24. And if I just bring the next equation, the first equation above that, see what happens is now I have the same number, 8x, -8x. So in this case, if I just add those two equations together, 8x's are going to cancel. 3y plus 20y is 23y. 1 plus -24 is really 1 minus 24, which is -23. Divide both sides by 23, and I get y equals -1. And so then I would plug this in to either equation. I don't like the one with negatives, so let's plug this into 8x plus 3y equals 1. So 8x plus 3 times -1 equals 1. 8x minus 3 equals 1. Add the 3 over. 8x equals 4. So x would be 4/8, which is the same as 1/2. So my solution is 1/2 -1. So you can multiply the equation by anything you want, and that's still allowed. Okay, so let's look at this next one here. Same situation. None of the variables seem easy to solve for without getting into fractions. But what I'm also saying is I can't really get what I want to try to do is get the coefficients to be the same, either positive and negative or both the same sign, because I can add or subtract. But I can't just multiply one of these by something. And so you're allowed to multiply both equations if needed to try to get the coefficients to be the same. So here's the options, and it doesn't matter which one variable you cancel out. For example, if I multiply equation 1 by 8, then this is going to turn into 72x. And if I multiply the bottom equation by 9, that's going to turn into negative 72x. And then I could add them together and cancel it out. And that would work. Alternatively, if I multiply this equation by 3, this is going to turn into negative 12y. And if I multiply this equation by 4, that's going to turn into positive 12y. And I could add them and they'll cancel out. Since this involves smaller numbers, I think that's what I'm going to do in this situation. So I'm going to times the first equation by 3. That's the whole thing. So this is 27x. So it's kind of like doing, you can do this if you want to, if it helps. You're multiplying the whole thing by 3. 27x minus 12y equals negative 3. And I'm going to multiply the bottom equation times 4. So I get negative 32x plus 12y equals 28. Then I could add them together. 27x minus 32x is negative 5x. That equals 0 when you add them. Negative 3 plus 28 happens to be 25. So if I divide both sides by negative 5, I get x equals negative 5. And you know what to do there. Plug it into either one. Let's just go with the top one. 9x minus 4y equals negative 1. So x is negative 5. 9 times negative 5 is negative 45. If I add 45, negative 4y, negative 1 plus 45 is actually 44, which is nice, because then if I divide both sides by negative 4, y would equal negative 11. So negative 5, negative 11 is my solution. Okay. So now, okay, so we've done some elimination. As I stated before, if one of the equations is easily solved for any of the variables, if you can isolate one of them, or if one of the equations literally is already solved for one of the variables, then it would be probably more efficient to use the the substitution method, meaning I can just take this, substitute it into the first equation. So I'm going to have 6x plus 3 times negative 2x minus 5 equals 1. That's going to give me 6x minus 6x minus 15. I'm distributing the 3 equals 1. Uh-oh, 6x minus 6x gives me 0. So I have negative 15 equals 1, which is clearly not true. So what does that mean? What is this telling me? Of course, that means there's no solution. And if you go back to the first page, what does that mean in terms of graphically? Both of these equations must be lines. If there's no solution, the two lines must be parallel. So these two equations, if we were to actually plot them, they would look something maybe not exactly like this, but we would see two lines that are parallel that are never going to intersect. I'll put lines parallel. But as far as our answer, we'll say no solution for that. All right. Let's look at number 7 here. We've got options here. It would not be too hard to solve the top equation for y without getting into fractions, and I could substitute it in. That would be fine. Why don't we do it that way since we solved the other one that way? So if I solve for y, okay, here's the way I do algebra, because if I move the x over, I'm going to have a negative y. And the quicker way to do it is, what if I add the y over here and subtract the 1 in its place, move it over here? So I'm going to add y. In other words, I'm going to flip-flop these, right? I'm going to add the y over here, move the 1 over there. That's going to give me 5x minus 1 equals y. And if I take that, substitute it in to the second equation, I have 10x minus 2 times 5x minus 1 equals 2. 10x minus 10x plus 2 equals 2. 10x's cancel. If 2 equals 2, or if I subtract 2 from both sides, I get 0 equals 0. Okay, we've seen this before. What does this mean? This is always true. And what does that mean now in terms of intersection points? What this means is, this is the case where these are in fact the same line, and so there's an infinite number of solutions. This is the same line, so there's infinite solutions. You can kind of see it here. If you were to take the top equation and divide each of these terms by 2, you see you get the same as the first equation, right? It's just a multiple of that. That's why there's infinite solutions. Right? Well, I said we don't like fractions, but sometimes you can't avoid them. You're going to have equations with fractions here. But as we have discussed earlier, you can, when you got fractions, there is a way, as long as it's an equation, we can get rid of the fractions. So how would I do that? Well, what's the common denominator for the first one would be 6. So if I multiply both sides by 6, 6 over 1, right? Not 6 over 6, what happens? Well, if I distribute, 6 times 1/3 is 6 over 3. That's going to give me 2x. If I multiply 6 times 1/2, that's going to give me 6 over 2, which is 3y. And on the right side, that's just 6. So what should I do on the for the second equation? If I want to get rid of that 4, I could multiply both sides by just 4. And that would give me 4x. When you do multiply 4 times 3/4, you can cross cancel the 4. You're just going to be left with 3y. 4 times 0 is just 0. Okay, then what I could do, I mean, you've got options here, but what I'm seeing is that since they have 3y in both of these, what if I just subtract these two equations from each other? 2x minus 4x is negative 2x. 3y minus 3y is 0. These cancel out. 6 minus 0 is 6. And if negative 2x equals 6, x should be negative 3. And let's plug it into either one. What if I plug it into the second equation? X plus 3/4 y equals 0. X is negative 3. Negative 3 plus 3/4 y equals 0. I could add the 3 over the other side. I could, okay. Oh, I could have probably plugged it in one of these, would have been easier, huh? But I didn't. That's okay. I could multiply both sides by 4 to get rid of the 4. Just 4 times 3/4, so you can cross cancel. 3y equals 12. So y would be 4. Negative 3, 4. One more thing. Since we had talked about graphing parabolas, we actually can also find intersections of other types of graphs. So you should recognize this is the graph of a parabola, this is the graph of a line. And if we want to find this common solution to this, it's equivalent to finding the intersection points. We would refer to these as a nonlinear system of equations, mainly because of this one, right? That's not a linear function, that's not a line. Okay. Just to review a little bit, for graphing, you should know how to graph the line, but let's work on the parabola here. I can find, for example, my y-intercept. If I let x be 0, both of those will be 0. I'm just going to be left with 5. If I want to find my x-intercepts, I can set my y equal to 0. That factors into x minus 1, x minus 5. If x minus 1 is equal to 0, x should be 1. You set this one equal to 0, you get 5. So I have 1, 0, and 5, 0. Let's plot these. 0, 5, 1, 0, 5, 0. So you're starting to see a parabola there. We can find our vertex using any of the techniques we've talked about. We can do completing the square. We could do, one of the things we talked about is the x-coordinate of the vertex is negative b over 2a. My b is negative 6, so it's going to be the negative of negative 6 over 2. My a is 1. This is positive 6 over positive 2 is 3. And if I want to find my vertex, I'm just going to evaluate that. Okay. Remember how we can, if we want to, we can call y f of x. So I'm really just going to be evaluating this parabola at 3. I'm plugging 3 in for x. 3 squared minus 6 times 3 plus 5. This is 9 minus 18 plus 5. Negative 9 plus 5 gives me positive 4. So my vertex is 3, negative 4. Negative 4. 3, negative 4. You should have probably known, remember the whole idea for negative b over 2a is knowing that if this is a parabola that's symmetrical, the x-coordinate of the vertex needed to be right halfway in between the two x-intercepts. So you could have probably also reasoned that it had to be 3 and then just plugged in to figure out the actual y value. Try my best to graph this. Okay, so there's our parabola. Our line right here, y equals 1x minus 5 has a y-intercept of negative 5 and a slope of 1. And remember, you can think of slope as, think of 1 as 1 over 1. So you're going rise over run to get another point. Up 1 over 1 to get another point. Up 1 over 1. So you're going to get a line like this, which clearly is going to intersect. I mean, we could probably, think about the graphing method to get these solutions, but we want to get these perfectly. I'm actually going to stop graphing this because I'm not quite so sure I did this parabola accurately. So but clearly it's going to intersect in 2 places, right? This line's going to intersect over here somewhere. So to find them, we want to do this algebraically. Elimination method's now out of the picture because we have different, we're not going to cancel out an x squared or anything. So what we're pretty much doing is just the substitution method. I'm going to, however you want to think about it, I'm going to plug this as y. I'm going to put that in right here. So I'm going to move this down. X minus 5 equals x squared minus 6x plus 5. I'm going to subtract the x and add 5. I want one side equal to 0. Plus 10. That factors x minus 2, x minus 5. So if this times this equals 0, it means x is either equal to 2 or x is equal to 5. And to find the y values, you can plug 2 and 5 into either equation. You can plug it into the parabola or the line because these are, in theory, these are where they intersect, right? So I find it's easier to plug it into the line. So if I plug in 2, 2 minus 5 gives me -3. If I plug in 5, 5 minus 5 gives me 0. So then let's go back to our graph here. That certainly looks like 2, -3, so that one looks accurate. And now I was starting to wonder about if this was really going to be 5, 0, and it does look like it. If you continue this, it's going to actually intersect the parabola right there. Just a preview of calculus. Why is this important? When we get to calculus, we will be asked at some point to find the area. We use some magical calculus to find the area between two graphs. And one of the questions you could get asked is to find this area. And there's a way to do that with calculus, but it starts with being able to graph the parabola, graph the line, to know exactly where they intersect, to know what this little picture looks like so we can see which function's the top and which one's the bottom. So this is all really important stuff as you move to calculus. All right. Thanks for watching. Hopefully this all makes sense.